Good morning, ladies and gentlemen. This is session V1LC, Acoustic Sensors. My name is Gijs Krijn. I'm one of the co-chairs, and I'm from the University of Twente, Mesa Plus Research Institute in the Netherlands. And my co-chair is...
My name is Jeff French. I'm from the Naval Research Lab in Washington, D.C., just south of here.
So we have a session with 5 papers. Up to now, the presenter for the second paper has not yet shown up, but hopefully he will enter in a few minutes or so. Oh, there he is. Okay. Okay, we first start with the first paper, now then later on you can upload your... Yeah, okay. So now I'd like to introduce the first paper. It is entitled A Free PZT Setup for Determining Physical Liquid Properties Utilizing Acoustic Pressure Waves. The paper will be presented by Antlinger, and the people are from the Johannes Kepler University in Austria and Vienna, the University of Technology in Austria. Please go ahead.
Ladies and gentlemen, welcome to my presentation about the 3 PZT setup for determining physical liquid properties utilizing acoustic pressure waves. First, I'll give a short outline of my presentation. I'll start with the motivation. Then I'll go over and present the sensor setup we devised, followed by a short introduction of the 1D model in the frequency domain. The next point will be the presentation of the measurement setup. After this, I'll show some experimental results, and I'll finish with the conclusion and the outlook of our work. So what was the motivation of our work? The measurement of liquid properties, like for example viscosity or mass density, utilizing pressure waves. We are looking to get a small, cheap and robust sensor. And what we also want to do is sensing the bulk of the sample liquid shear wave approaches. Due to the small penetration step, only sense a small area around the sensor, and with a pressure wave approach we can sense the bulk of the probe. We note that when we utilize pressure waves for sensing the viscosity, not the shear viscosity is sensed, but the so-called longitudinal viscosity. And special with this sensor setup, we want to eliminate the dependence on PZT parameters, which usually show high spreads in the parameters. Application examples for our sensor could be liquid condition monitoring or online process monitoring. So first I would like to show you a 2 PZT sensor setup, which is shown here. This setup can be operated in the frequency and time domain. Frequency domain means that you use a continuous wave excitation signal, and time domain is using burst signals or step signals. For this setup, the PZT parameters have to be established firmly, and typical spreads of PZT parameters are 5 to 25%. What we mean with PZT parameters is the material data you get from the manufacturer. And the fluid damping, which the excited pressure waves see on their propagation path from the transmitter to the receiver, is a measure for the so-called longitudinal viscosity. So we expanded this setup to a 3 PZT setup. This approach is also based on monitoring the attenuation of the pressure waves in the liquid sample, which is contained in the sample chamber. We have 2 planar in rigid boundaries which form the sample chamber where the liquid is enclosed. Each boundary carries a PZT transducer which is acting as receiver. As you can see here, due to the mounting, the receivers are backed by air, which yields in a low but defined acoustic backing impedance. And one PZT transducer which acts as transmitter is mounted in the sample chamber. So both faces of the transmitting PZT discs are facing to the surrounding fluid. The transmitter now excites pressure waves of ideally equal amplitudes in both directions towards the receiver discs, and due to the different lengths R1 and H2, the propagation, the viscous attenuation along the propagation paths give a measure for the attenuation alpha, which is given here. You see the attenuation alpha depends on the mass density of the fluid, on the sound velocity, on the excitation frequency, and on this term the so-called longitudinal viscosity, which is a combination of the shear viscosity and the bulk viscosity. As we use burst signals for driving the transmitter disk, interference effects due to reflected waves are avoided, and if we have three identical PZT disks, the electroacoustic conversion coefficients cancel out. So we are no longer dependent on the PZT parameters in an ideal case. Now I would like to show you a simple 1D model of this sensor setup. For the fluid, we use acoustic transmission lines. You can see here the acoustic transmission line 1 and the acoustic transmission line 2 with a characteristic impedance which is due to here. It also depends on the mass density, the sound velocity, the frequency, and this term is another notation for the longitudinal viscosity. Mu is again the shear viscosity, and lambda is also a measure for the bulk viscosity. Unfortunately, in the literature, there are different notations for the bulk viscosity. There is one common term is 2 times mu plus lambda, and the other one is 4 times mu divided by 3 plus the bulk viscosity. And this is the propagation constant of the acoustic transmission line. For a PZT transducer, we use a standard 3-port model, which has 1 electric port and 2 acoustic ports. And if you use continuous wave excitation signals, spurious interference effects occur, so we have to use transient signals. So this model is suitable for simulations in the time domain. If you use transient signals, like we do, you have two possibilities. You make the simulation either using an FFT approach to obtain transient simulation results, or you can use a simulator which is suited for transient simulations, like for example PSpice or PSpice. Now I would like to introduce our measurement setup. We have a modular sensor chamber which consists of aluminium building blocks. For this setup shown here, we get distances, for the two distances between the transmitter and both receivers, we get 22.6 millimeter and 31.6 millimeter. All three PZT transducers are big 255 PZT discs with a diameter of 25 millimeter, a thickness of 0.5 millimeter, which results in a resonance frequency of about 4 megahertz. The both receiver discs are flush mounted on 1.5 millimeter FR4 standard copper coated PCB material. I would like to show in detail the mounting of the PCB transmitter. You can see it here, the disc. We glued it to a symmetrical arrangement of suspension wires. These suspension wires, you can see, are on the front and on the back side, which are so they are parallel, that we get a symmetrical mounting of the transmitter, and the electrical connection to the outer world is provided by an SMA connector, and here we use thin wires for the electric connection, which are soldered to the electrodes on both faces. Now let's move to the experimental results. Here is a lot of text, which I will explain on the next slide with pictures. We used an Agilent 81150A signal generator as signal source to drive the transmitter with a sine burst of 20 cycles and a frequency of 2 megahertz, which is not the resonance frequency of the PCB transmitter. We recorded the transmitter and both receiver voltages with an Litroy wave runner oscilloscope. As test fluids, we used distilled water at the temperature of 20 degrees and S200 viscosity standard oil in a temperature range from 15 to 45 degrees with 5 degrees step. Then we signal processed the recorded data in the time domain, which means that we removed unwanted data like triple transient response or transient settling signals of the PZT disks by zero padding. And as last step, we made an FFT spectrum of the processed data in the time domain to get a measure for the damping. Here you can see, for example, the measured transient response for the sample chamber when it's filled with distilled water. You can see it on the left side, and with S200 viscosity standard oil at the right picture, both at the temperature of 20 degrees. As expected, as water has a much lower viscosity than this S200 viscosity standard oil, you can see that the damping in water is much lower. For example, here you can see clearly the triple transit response, and you can also see the transient settling of the PZT disks, which is not so clear to see when the viscosity is higher, so you have to zoom in more. So this was the original recorded, or these are examples for the original recorded data of the measurements. Then, as I showed you a few slides before, we process the data in the time domain. Here you can see the original measurement data for the sample chamber filled with water. And here you can see the process data. So we remove this transient settling and we remove the triple transit response. So we get the data we want for our FFT. Here is an example FFT spectrum for S200 viscosity standard oil at 20 degrees. We evaluate the values at 2 MHz, which is our burst signal frequency, and this difference gives a measure for the attenuation. Here you can see the input, the spectrum of the input signal, and these are the spectrums of the two output signals. And this difference gives a 2 MHz gives a measure for the attenuation. If I would show you the spectrum for water, both curves would be nearly identical. There's only a small difference. So this is the summary of our experimental results for the S200 standard, viscosity standard oil. We assumed a ratio from eta bulk to U, from bulk viscosity to the shear viscosity of 1, which is given in the literature for this kind of fluids. Of course, this is not the exact value. It was a publication from the year 1965 where they made, this was one of the publications we didn't find any newer. And of course there's also a temperature dependence. So it is clear that both curves can't be exactly the same. We also neglected the fraction effect. And here you can see the formula for the measured attenuation. So it's calculated out of the FFT spectrum we obtained at the burst frequency of our sine burst, and this is the theoretical value depending on the fluid parameters, mass density, sound velocity, and the longitudinal viscosity. But both curves show the same tendency, and we hope that with our future work, which I will present now in the conclusion and outlook, we will come to a more to lower the differences between the two curves. So we investigated the feasibility of the three PZT setup configuration, utilizing the transient pressure waves for determining physical liquid parameters, particularly in our case the longitudinal viscosity. We introduced the basic sensor concept and an according 1D model. The experiment data we got with our measurement setup confirmed the expected behavior of our sensor setup. What we also have seen is that our model needs to be refined in order to get more accurate measurements. For example, we should incorporate the fraction effects, and further investigation of the obtained experimental data will be included in our future work. So I want to thank the sponsors of our work, which is the Austrian Science Fund and the Austrian Comet Program. Thanks for listening.